Section 2. Introduction to Cosmos-SDK and the Interchain ecosystem. As we defined previously, a blockchain is a replicated deterministic state machine, where we can start from a state S, and we apply each transaction in a block using a state transition function, and we reach a new state of the chain called S prime. The Comet SDK provides maximum flexibility to define our state of the application, the transaction types, and the state transition functions. This SDK is usually used to build sovereign, interoperable, application-specific Layer 1 blockchains, but nowadays, this technology can be used to build much more than that. Regarding the architecture of a Cosmos SDK chain, there are two main blocks. One is the Cosmos SDK application, where we have our state machine and our business logic. And then we have the Comet BFT, previously called Tendermint, that is in charge of the consensus and networking layers. Let's look a little bit deeper on each of these blocks. Regarding the Comet BFT, previously Tendermint, it handles the state machine replication over the network. It is application agnostic and is communicated with the application using this ABCI, which is the application blockchain interface. This means that any application that complies with this ABCI, it would be suitable to use the Comet BFT consensus engine. There are participants in the protocol that are called validators, and these are the ones that take turns proposing blocks of transactions and voting on them. The consensus algorithm used in Comet BFT is a proof-of-stake algorithm. This is how it looks, the Tendermint or Comet BFT consensus algorithm. It starts with a new round where a new block proposer is selected in a pseudo-random fashion. This block proposer proposes a new block with certain transactions, and it is broadcasted to its peers that are the other validators. Those other validators are going to pre-vote on this new block. They can pre-vote nil if they find an invalid block, or pre-vote the block that it is a valid block. Once we wait to more than 2/3 of those pre-votes, once we reach this 2/3, then we get into the pre-commit stage, where each of the validators pre-commit the block, depending if they find it to be invalid or not. And once we reach more than 2/3 of the pre-commits, we commit the new block and we create a new height, and that's how a block is created in this kind of chains. Keep in mind that when I'm saying here more than 2/3 of the pre-votes or the pre-commits, it refers to the staked amount, not the number of validators. So for example, if we have 10 validators and within the first 3 validators we have 70% of the voting power, only having a valid vote from these 3 validators would be enough to create new blocks. Another key component of the architecture is the application blockchain interface. That is an interface on the Comet BFT that allows to communicate the state machine with the consensus and networking layers. Comet BFT only handles transactions in bytes. It has not knowledge of what these bytes means, which gives it great flexibility for the application developer to do whatever they want in the application layer. There are a few messages defining this interface. Some of these, the most used, are the finalize block, that performs transactions validation, but the application against the current state, the application protocol, and the cryptographic credentials of the transaction. Then there's also the check transaction that is used to validate the transactions that are submitted by users, and only the valid ones are relayed to the peers. And then there's also the commit message that is used to compute the commitment of the current application state that to be placed on the next header. And this is how it looks, the communication between the application and the consensus logic. You can see here on this side we have what would be the commit BFT with the consensus and networking, and here we have the application logic, and these two communicate. For example, in this case, a new transaction is submitted by a user, so there's this check transaction ABCI method that is called, that is sending the transaction to application to check it, and the application is returning a result, and the same for submitting a new block. But we will dive deeper on this in Module 3. This is how the whole interface looks like, the IBCI. In this case, we have the IBCI++ or V2 that introduces a few new methods like prepare proposal, process proposal, verify vote extension, and the finalize block that previously you may see in the literature. Other methods like begin block, end block, and deliver transaction, and these are all private within this finalize block. Also, you have the query method that is used for queries and check transactions, that the one that we previously saw how it works. But yeah, we will go through this more in detail in Module 3. Regarding the Cosmos-SDK block, here we have this framework that facilitates the development of secure state machines on top of Comet BFT. Regarding the main components of the SDK, we have the base app that is basically a boilerplate implementation of the IBCI in Golang. And this base app is going to be wrapping the modules and our application-specific logic to be able to communicate and replicate our state machine over the network. Another key component of the SDK is the multi-store. That's how we persist data in the SDK. That is a store of stores, and these stores are key value stores. The modules are the backbone of the Cosmos SDK. Cosmos SDK applications are built by aggregating a collection of different interoperable modules. Each module defines a subset of the state and contains its own message and transaction processor. These modules can be considered as small state machines because they will be handling themselves their own state. And the Cosmos SDK routes each of the messages that it receives from users to the corresponding module. So in this figure, we have an example of a finalized block IBCI request from Comet BFT, and we can see that in the base app, we decode the transactions, we extract all the messages, and depending on the message that we have a router on this base app, and it will route the message to the corresponding module, in this case the governance module, handle the message, and return a result. As I said previously, each module can be seen as a little state machine because they handle their own state, and each module declares its own key value store in the multi-store to persist their state. Actually, per module, you can have as many stores as you want, but usually you have this pattern of one store per module. And the keepers are the main component of the modules, that these are the gatekeepers to their state. You can only access a module state and modify it using a keeper and its keys. Let's talk a little bit about the Interchain ecosystem. So far, we talked about building a blockchain, but we didn't talk about smart contracts. You can enable smart contracts on your blockchain using Cosmos, that is a framework for building WebAssembly smart contracts for the Cosmos SDK. Another key component of the Interchain ecosystem is Inter-Blockchain Communication Protocol, or IBC. IBC leverages the instant finality of Comet-BFT consensus algorithm to allow for the transfer of value and communication between heterogeneous chains. By communicating different chains, these concepts of zones and hubs arise. A zone is just an app chain that can be communicated with other chains, and a hub is a blockchain that is designated and designed to connect all the zones. We can see this concept in this figure where we have the zones at the edge of the network, and each of these zones can be connected to a hub that connects to another hub and connects to a bunch of other zones. Consider that each of these zones and hubs are chains built with the Cosmos SDK, or in this case can be other type of chains like Ethereum or Bitcoin, where we need some kind of wrapper to implement the IBC protocol to connect with these other chains. Another interesting concept developed in these last few years is interchain security, where there is a provider chain that provides security to another chain that is called a consumer chain. This allows Cosmos blockchains to lease security to each other. For example, we can have the Cosmos hub that its validators are used to secure other chains like Proton and Neutron and Electron. In order to launch a blockchain using this scheme, you have to submit a governance proposal on the Cosmos Hub to make this happen. Some use cases within the Cosmos SDK, well, most of the use cases are mostly the same use case as blockchain in general, with the additional component of this interoperability and secure communication between chains. We can build decentralized exchanges, DeFi protocols, open marketplaces, and a game economy. One of the most relevant built with the Cosmos SDK are the BNB chain from Binance and Chronos chain that it's used for in Crypto.com. That these are two big central exchanges, but there are actually quite a few Cosmos SDK chains that you can see in this figure. In fact, if we go to this map of zone site, we can see live how all these are connected and are communicating via IBC. So as you can see, there are a lot of chains right here, and each of these have its own use case. For example, Osmosis is a DEX, Noble has a native USDC, Celestia is a data availability layer, Evmos is an EVM chain, and we can see that these are all interconnected, and we can actually see live each of the messages going out on or in to these chains. Well, that's it for Module 1. Let's wrap it up.